All right, so we need to find the average power dissipated in RL. So this is similar, except for the fact that it's asking about average power. And if we think about what I was just showing you a minute ago, the average power is going to be the real part. So let's see. Let's get everything from here to here, get the Thevenin equivalent of that. So we could do, okay, so the first thing to do is the source transformation, where we change the voltage source to a current source. So I did that here. And then we combined R1 and R2 in parallel to get R1, R2 over R1 plus R2. So now I have a circuit that looks like this drawing right here. But remember, we're looking at this from the point of view of our load over here. So if I want to get the Thevenin resistance from that load, then to see what it looks like, I deactivate my power sources. So I have this resistor and the inductor are in parallel with the capacitor from the point of view of the load. And so my Z total is ZL in parallel with R1, R2 over R1 plus R2 plus ZL, or ZL, which is 0.8 kiloohms, times R1 is 1, R2 is 0.6, that's 0.6 over 1.6 plus, well, this was ZC, that's ZC, and ZC is negative J.5, this was J, 0.8 J, and this is negative J.5. It's in parallel. This is J.8 in parallel with this right here. So that's J.8 times 0.6 over 1.6, which is 0.375, minus J.5 over J.8 plus 0.375 minus J.5.
This is on recording.
Yes, it is recording now. Yeah. You're welcome. And now I'm just going to say this for anybody who's watching this. I'm now sitting in this room all by myself recording this video just for y'all. Anybody walking by, you'll see me talking to myself. That's all right. Thank you very much for coming.
Of course, thank you.
J.5 over J.8 plus 0.375 minus J.5. does not seem right either. Let's see. Let's see where I went wrong. So where I went wrong is I got my numbers for my capacitor and inductor backwards. So ZC, yeah, it's because I can't write a C or an L correctly. Well, I write them both the same. And of course, the capacitor should have the negative, the imaginary part should be negative. So this one should have been minus 0.5. And this one should be plus 0.8 and plus 0.8. And so it's minus 0.5 plus 0.8 minus J.5 plus J.8. So then I'll go up here and edit this. So that one will be correct, but this one needs to be plus 0.8 and minus 0.5. And is that correct? I believe it is. It is. Okay, so this gets us a total impedance of 0.406 minus 0.8 minus 0.8 something minus 0.825J. And that's in kiloohms. So in ohms, it's 406 minus 825 minus J 825 ohms is my total impedance, my total Thevenin impedance. Okay, so now to find V Thevenin, that would be, looks like it's just, let's see. So V Thevenin is V open circuit. So V open circuit, so let's think about what that would be. I would have my V that we found before, which would be V times R1, R2 over R1 plus R2. And then I have this impedance that we just found, 406 minus J 825. And so V open circuit is going to be nah, it's not going to be that because well, let's see, where would it be? So it would be here, here. V open circuit would be V across the capacitor. Okay, so we got R Thevenin, and now we're going to find V Thevenin. And to find V Thevenin, I'm going to go back and look at my original circuit. And here is our load. Now, I did not have it on the problem sheet, but this was supposed to be 100 volts. And this was 1,000 ohms. And this is 600 ohms. And our inductor is J800 and our capacitor is minus J500. So if the first thing we do is a source transformation on these two, then our current source will be V over R. 100 divided by 1000 is 0.1. And I have 1000 here and 600 here. And then 1000 and 600 in parallel. So 1000 times 600 over 1600 is 375. So that's 375. So let's not bring it out yet. And there's RL. Okay, so now if I do a source transformation again, change this back to a voltage source, 0.1 times 375 is 37.5 volts. This is 375 ohms. This is J800 ohms. And this is minus J500. And then here's where we have RL. Okay, so now I'm just going to call this, for simplicity's sake, I will call this Z1, and I will call this, actually I won't call that anything, but I will call that Z1. So then if I do a source transformation again, I would have a current source, which would be 37.5 over Z1. There's Z1. And here is ZC. Now if I combine those in parallel, 37.5 over Z1 RL. So this is Z1 ZC over Z1 plus ZC. And then if I now do a source transformation again, I will get 37.5 over Z1 times Z1 Z2 ZC over Z1 plus ZC. And this, of course, was our Z Thevenin that we found before. And so what we have over here, Z1, ZC, Z1 plus ZC, that is our Z Thevenin. If you go back and look, right here, it was these two things in parallel. Which is what we have here. And so now I can say this is 37.5 over Z1 times Z Thevenin is my voltage, and Z thevenin is my resistance, and then I have, this is R load, I have my load. So this is 37.5 over Z1. Now what was Z1? Z1 was 37 plus J800. Wait, no, it was 375 plus J800 times Z thevenin was 406 minus J825. So that will be times 37.5 over 375 plus J800 and I get V thevenin to be minus 24.39 minus J 30.488 volts. Alright, so now I needed to get the average power dissipated in RL, so I want the real power. So remember, power is 1/2 V I conjugate, is that V thevenin is minus 24.39 minus J 30.488. We have that Z thevenin is $406.5 minus J825.2. So we have Z thevenin, V thevenin, and we have our load right here. So what would our current be? Our current would be equals IR, I equals V thevenin over 406.5 minus J 825.2 plus RL, which they give us is 3 kilo ohms. So this is just V equals IZ. So the current through this would equal that. So I will equal V thevenin over that. So I will equal minus 24.39 minus J 30.488 over 406.5 plus minus J 825.2 plus 3,000. So I get whatever current that is, minus 0.0047 minus something. Minus 0.0101, J 0.0101. Now I know that my power is 1/2 times my voltage times the conjugate, but my voltage across this would be only part of the voltage. So to find the voltage across RL, you would just use Ohm's law and say that voltage is just the current times the impedance, and so that equals 1/2 ZL times I times I conjugate. Now, I conjugate is, well, I times I conjugate, well, that's the definition of the magnitude squared. So the magnitude of anything squared is that thing times its conjugate. So this is probably one of the formulas that you have, but times I conjugate squared magnitude. So if I take my total power is 1/2 ZL, now that's real, it's 3,000, and then the magnitude of the current squared, that's also going to be real, so that will be the square root of 0.0047 squared plus negative 0.0101 squared, and that whole thing squared. Or we can just do that on the calculator, and we can do let's see, I think that's our current up there, so I can go to second complex, get magnitude, and I'll get the magnitude of our current, and I'll square it, and I'll multiply that times the resistance, which is 3,000, multiply that times 0.5, and the real power is just the real part of this, and that is, it's real, so we don't need to find any other part of it. That is it, so it's 0.186 watts. So our average power, which is the real part, 0.186 watts.